this thing, where here, or there, consists of functions that are invariant under any of the derivations on x. That is, they're the constants. Here, because my y might have additional constants in it, where the y is an open, I might have additional constants there that I don't have for x. So this being a sheaf might have values different from the base field in the PV setting. But I'm claiming that this is exactly analogous to this. So this should be the Poincaré lemma. Now, I saw a very nice note by Chambert-Loire this summer, because we tried to prove something like this for quite some time last year. And there's this note of Chambert-Loire where he talks about crystalline cohomology, where in a paragraph he proves Poincaré lemma by the following technique. If this is free, the base is dx1 through dxn, then each of these successive ones is free also. And it just involves taking combinations of the dxi's. And so inductively you can strip out one variable at a time. And then you can calculate what happens. And it turns out the induction step is absolutely straightforward. The induction step immediately gives you Poincaré lemma. So you're left with the case n equals 1. So I thought we were done until, after having written the abstract, I sat down to try and write the details. What happens at n equals 1? Well, I've got some ring B. So this is the open in some y over x, but it's an affine. I've got just one coordinate function I have to worry about. I'll call it dx. And I have to show this mapping is onto. Well, I only have one derivation here. So I have to solve the equation d dx of f equals b. The problem, though, is I have to do this in the PV site. So I need an extension of B which has not just d dx, but has dd, all the others, in it. It came from my base scheme X. So it doesn't have to have all the possible derivations of B on it, but it has to allow me to extend ddx, ddx2, ddx3 out to ddxn. And I don't know what those conditions are. You know, obviously to try to make it integrable, I would want ddx2, that's ddx2 of b, to be the same as ddx of ddx2 of f. But I don't know what ddx2 of f is going to be. So there's an integrability question there. And it's one we've been stumbling over, and Chambert-Loire's argument reduces us to being able to solve this in the PV topology, but that's not the same, unfortunately, as being able to prove this. So at this point, this is conjectural. Nonetheless,
So
yeah.
So the simplest form of the Poincaré conjecture is the fundamental theorem of calculus. right?
Poincaré
The
lemma.
section, yeah, the lemma, right? And it has an n-dimensional version, right? So, did that help you there?
No, unfortunately. I want to think about something like that, because I think what's not clear is it's not clear that it's a PV open. But I could, I could solve this, I think, but with power series.
Okay.
But it's not clear that the resulting solution is definite. I mean, the problem seems to be that, you want the mixed partials to agree. So I can get the partials of B, but I don't know what the partials of F have to be.
Can you modify the PB?
Well, if we have to.
Works for that.
Maybe if we have to, but we don't want to. I mean, Carlos was thinking that this was a PPV kind of question. In some loose sense it is, because the other derivations just don't appear. The ddx2 out to ddxn just don't appear. But we were never able to find a good solution. But at least Chambray-Leroy's comment reduces us to this case. If you can do this one, then we can do this. And basically using the fact that the basis here determines the basis all the way out. And you can evaluate what the differentiation is throughout. All right. Now, however, all is not lost. Because there are some consequences that immediately flow out of this. The most natural one is this. So Z1 consists of the closed one forms. And what I'm asserting here is that if you give me a closed one form, then I have enough conditions here so that this doesn't arise. So I can directly find a PV opening mapping to it in which there's a function with differential as this. So the closed one forms are the image of function in the PV site. This is an exact.
For which x?
X smooth. The X is always smooth. Well, so a consequence of this is that HP, HI, so Grothendieck showed that the hypercohomology, which I unfortunately just erased, the Drom complex, you can do that algebraically as well as analytically. And the algebraic and analytic values agree. So for smooth varieties, you can calculate the de Rham cohomology by taking the hypercohomology of the de Rham complex provided X is smooth and projective. I had to add the word projective, but that's good. Because if it's projective, we also know that those E2 terms agree analytically and algebraically. The cohomology of the P forms analytically is the same as cohomology of the P forms algebraic. So this gives us a way of getting P sub it. If we had this result, I could put a star here and a star here. And we would have, in the PV site, a way of getting at the de Rham cohomology of a smooth variety X over any field. Well, I guess so much for the first part. The second part is just lots of big diagrams. This is big enough for the first one. So this is the Grothendieck period conjecture. GPCK. So in the paper where Grothendieck shows this fact about the de Rham cohomology of projective smooth varieties being the same as the analytic one, stronger statement than that, but that's all I want. He asks the question, what happens? How to interpret cohomology classes here. In here, the Hodge conjecture says that the PP classes should be algebraic. Well, if they're algebraic, if they come from cycles on X, then I ought to see that in the HQ, the cube singular cohomology. So the diagram that's being used now is like this. So I take X. Now, remember, X is defined over some field K. So when I write it this way, I mean I'm extending the field to the complex numbers. So this sits inside of the singular cohomology. This is the one that's isomorphic to the de Rham cohomology. Wait, I don't want to see there. But this is the one, this is the de Rham cohomology in the analytic setting that Grothendieck showed is really the hypercohomology of well, let's make it this precise. So I'm going to take X defined over a number field, and I put it over the algebraic closure of the number field. So here's my de Rham cohomology over the algebraic closure of Q. It maps to this one, which is the de Rham cohomology over the complexes. And so the question is, now, I lied to you, and I don't have time to explain it all. But I'm going to have to twist this because when I look at the exponential sequence, you think you get 0 to Z to O, exponential to O star. Well, that's not true. It's exponential 2 pi I. So I want just the exponential there. I want to put that 2 pi I in the Z part. So I'm going to multiply this by 2 pi I. Well, let me not do it here. All right, see, I'm going to twist it, so I got to define the cohomology of X. You know, the Q of K. That's going to be the singular cohomology of X. Times 2 pi I raised to the K. Over here, it doesn't matter, because the coefficients here are complex numbers. But to make everything balance right, here, my coefficients are rationals. I got to have that 2 pi I there. So that's what this means. All right, so we define H2K Rothenbeek X Q of K is going to be H2K C. Now, 2K rom X over Q bar. My X is defined here. So classes here should be derived classes that where I don't need the full complex numbers to get at. And also in H2K X and C Q of K. So we're defining, this intersection, of course, takes place via this diagram. So the element here is something H2K Q, when multiplied by 2 pi I to the K. When I go over here, I get some element comes from here. So it's a parabola, something from here, which agree over the complex numbers.
So that first thing on the right-hand side, the DeRom part over Q bar just means what you get from the hypercohomology?
Yeah, this is, that's the hypercohomology. And I'm using this just to indicate I'm doing over Q bar. Now, obviously here, I need the 2 pi I comes in because I've got to relate this one to this one. And I do that over the complex numbers. The period conjecture is a map from cycles of codimension K to this cohomology group. This is on too. So all of this kind of material is in this book by Andre on motives that he wrote in 2004. So I understand that there's going to be a new edition coming out shortly. It's also in a paper on the archives by Bust and Charles from last year. if K is 1, H2 Grothendieck, something H2x, H2 de Rham of x. That's the one where we have this direct sum decomposition is H20 plus H11 plus H02. And it's in H2 of x singular cohomology with Q times 2 pi I. So that's the one case where the Hodge conjecture is known. So now I'm going to take x to be something, algebraic over with complex numbers, conjecture smooth. When I look at it in the analytic sense, I can do exponentials. So on x, on the analytic topology, I have a sequence like this. I'm putting the 2 pi I here because I don't have exponential of 2 pi I f here. I just have plain exponential. I take the cohomology of this, I get here's pig x. In codimension 1, cycles codimension 1 are divisors. So these are the ones of codimension 1. They go, this is the first Chern class, into the H2. And then they go to 0 here. Well, if they go to 0 here, remember, this is part of that direct sum decomposition of the H2 with complex coefficients. Furthermore, Deline's argument says H2 0 is conjugate to H02. So if this element goes to 0 here, its conjugate is 02. Its conjugate is 0 also. So that means this element here has to land in the 1-1 forms. So the image of pick in here, when I look at it in the complex numbers, I don't have quite enough space. Sits inside the 1-1 forms. And if I have a 1-1 form, how do I know it comes from here? Well, if it's a 1-1 form, it's going to go to 0 here. And if it comes from Q cohomology, up to some multiple will come from here, which goes to 0 here, so it has to come from here. So very roughly, that's the argument for why the Hodge conjecture holds in codimension 1. No, we got got this thing here. What I haven't yet written down is there's a comparison theorem. In PV cohomology, if I have a projective smooth thing over complex numbers, think of it analytically, I could put the PV analytic topology on there. The PV analytic topology would mean adjoining solutions, differential equations. And it's sort of a formal consequence that I can already solve differential equations, locally in the analytic topology. So the cohomology in the PV analytic topology is going to be the same as the cohomology in the analytic topology. So this cohomology in the analytic topology is just this one here. And then we have a site comparison theorem from the analytic PV to the PV, and because it involves just solving differential equations, which we can do in both places, that is an isomorphism also. So I claim that this cohomology of this one here agrees with the cohomology of X with complex coefficients in the analytic setting. Now, Carlos hasn't written that out, but we're essentially believe that comparison theorem is true. This then tells me if I take the PV cohomology here, it's really basic extended complex numbers. So instead of working with a hypercohomology over here, this is just tensing it over Q bar with C. And the claim is that is invariant under the actions, under automorphisms of the complex numbers over Q bar. Now you remember, Deligne's argument said that complex conjugation had very real impact in terms of the Hodge cohomology. It's not at all obvious. But what we're claiming is, at least in the case of H2, we have an invariant map from here to here. Invariant under automorphisms of the complex numbers over Q bar. So in this period conjecture, this one here, when K is 1, it's just this group here. And all you're doing is tension of the Q bar with C to get to this one. So this suggests we have a very real piece of information because we can see in terms of this cohomology how automorphisms of the complex numbers that fix Q bar, how it acts. In fact, to prove the growth of the period conjecture in codimension 1, all we need to do is show that somehow elements in here, which have a filtration coming from the spectral sequence, lie only in piece 1-1. Now I say only, we haven't done that yet. but I think that really ought to be a way of seeing the codimensional case of this. Now the work of Boston Charles, they prove the conjecture in codimension 1 for products of curves and abelian varieties. And I think that hopefully with a little effort, we'll be able to extend that. And then if we could do the Poincaré lemma in full force, if we could solve that question I raised, then we could formulate the GPCK in terms of this group, where we have 2K here, so that you see where the action of C over Q bar is. So that's sort of the ultimate goal. There is, of course, variance on this conjecture. I mean, this relates singular cohomology to Durand. There's a variant due to August that relates singular cohomology to a tau p-adic over a p-adic field. You know, basically, Grothley's question is, I've got all these cohomology theories, they ought to be connected. And the heart of it are these cycles, which I didn't really define, cycles of codimension K. They have to live in the Q cohomology, and that forces them to be in the 1-1 part here. So.
You are the organizer.
And
No.
So,
Any questions?
suppose you prove it. Suppose the conjecture, whatever, of the differential Poincaré Lemma is true. What exactly is the effect on the solving equations, differential equations, linear differential equations?
Could you ask that louder, William? I couldn't hear you.
Okay. All right.
Or could you repeat the question?
Okay. I'm asking, suppose the differential Poincaré lemma was proved, and what is the effect of it on solving linear differential equations?
Minimal. I mean, it's an application of the theory, really.
This is an application to algebraic geometry.
To what? You mean application of the differential, this machinery?
Yeah, yeah.
I see. But you don't know what it really means?
Well, there's some other stuff.
I mean, for example,
involves some stuff.
For example, the non-differential version of Poincaré lemma, is about generalizing the fundamental theorems. So you do it in this vector form.
Yeah, but what is it? What is the application of that to linear differential equations?
No. The original one is not for integration, but for integration. So,
Yeah,
for example, a scalar field is always divergence of some vector field.
Well, this really sort of is outgrowth of the stuff on differential Brauer groups. This is the second application. And sort of what I really would like to be true is I would love to be able to do differential geometry,
Yeah.
differential algebraically.
But aren't you really working in with algebraic schemes throughout this?
Oh, yeah.
Not,
That's why I said it's
not
Williams'
differential
differential varieties.
Yeah, so
Yeah.
it's differential structure.
Right. But it's bringing in.
Of an algebraic variety.
You see, what I think is really interesting about this is this gives you a way of seeing what happens over a number field.
Yeah, I was interested in.
which you don't have.
Right, which I'm running into.
That you have it through this hypercohomology. But the hypercohomology, the action of automorphisms of complexes over Q bar is sort of totally mysterious. It witnessed Deline's lovely argument. So it seems to me that this may well prove to be a useful tool in number theory,
Yes.
being able to get at some questions about that.
In the case where you were stopped, if you had more than one derivation operator, what if you're dealing with over-ordinary differential fields, does everything go through?
Oh, yeah, but then none of this stuff is of interest.
Oh.
Because you talk about curves. And for curves,
Yeah.
all this stuff is really trivial. And that's where Boston Charles stopped when they proved this in codimension 1. For a curve, there's not much there to the conjecture. Because when k equals 1 on a curve, that's a point. And so exactly, it's on because H2 of this thing, well, H2 of a curve is just Z. So I do H2, my curve, it goes to Q, I get Q.
I see. So the X sets the whole differential theory.
Right,
You're not ever looking at curves on higher dimensional varieties. So you
right,
use
right.
ordinary differential.
Yeah.
fields.
Do you have moments when you think that the conjecture is not true? I don't
Carlos introduced an example that I found very worrisome because it deals with the incomplete gamma function.
Oh. With what? The
Incomplete gamma
Oh, the
function.
incomplete gamma?
But I don't
Your
really see
favorite.
why
Is
it
it
should be
ugly
true.
then?
It seems to me what you need to do is impose some extra conditions on your setup to make it true. I don't really see why it should be true.
Well, it may
would
be.
nice, I would agree
Yeah.
with that.
Yeah, it seems to be trapped between the idea that analytically you're getting power series expansions and that tells you what's going to happen.
Yeah.
And algebraically, you just don't have quite enough information. And the solution to that seemed to me to be do power series,
Yeah.
but we were doing it on a PV site rather than on just the general differential flat site.
Yeah.
But I think that this application, if we can show that it's of type 1-1, and that's a thing I've been thinking about it for a while,
Yeah.
and it's not at all obvious that it has to be. But it has, you could, given something here in H2 growth index, you can, sorry, I said, in here, you can relate part of it being in 1-1 type.
Okay.
That part you can hit easily. So you can assume that the class you're looking at here has no 1-1 component in it.
Yeah.
So it's invariant under complex conjugation, though, because it has to come from here. And how do you use that to get a contradiction? It's not. I mean, if there were obviously, I think, I don't know. I'm always reluctant to say somebody really smart would have done this before. But it just seems that allowing yourself to solve differential equations is sort of a natural extension to atomic cohomology. And that this is the kind of application that ought to be.
Oh, so the cohomology of the PV works for the complex coefficients. That's your motivation too.
Yeah.
But then how about
Right.
finite fields or other?
Right.
Because the étals is the opposite.
Right.
Yeah.
I thought a little bit about that this summer. And then I discovered that apparently Berthelot wrote 2 books, one of which I have, but didn't have with me. Because there the issue, the question I was looking at this summer was not that broad, but it's more, if I have a, what do you call them? Those things, maps to power series rings? Higher derivation, an iterative. If you have an iterative derivation, you know, somehow that's too much information. All you really need is the stuff at level p, p squared, p cubed. And so somehow I was thinking that the bit vector should come in there because the bit vector, differentials of the bit vector come into through the de Rham-Wick complex into crystalline cohomology. So I spent time trying to think how in characteristic P you could do this. The point being is that bit vectors, you have multiplication by P. So what it should do somehow is shift you from the first derivation to the one for the P powers. But as I said,
Computer.
you know, it's just vague thoughts at this point. But yeah, I mean, I think that that's a natural question to ask is, what's the setting look like? Because there's a lot of work being done now. P-adics. But it's going to have a totally different flavor. And I think that something like the big vectors is going to come in to mix all those derivations together. And there's a Hasse-Schmidt exponential map, which takes you from bit vectors to power series rings over the bit vectors. That lets you do exactly what you want to do with a derivation in characteristic 0. You exponentiate d1. So you can do the same thing over rings where P is not a unit, but all the other relative prime integers are units. There's an exponential map there, which ought to play the role. Ought to, I say. Well, I was worried about how to do this, so I got to go home and read Berthelot now.
What's the motivation for this growth time period conjecture? Why is doing this?
Well, his feeling was somehow that a motive should be the very base cohomology theory. And everything should flow out of that. So here's one cohomology theory, here's another one. And this formulation is not what he formulated. He just asked a question, you know, what's the relationship here? I forgot the exact form of the question, but he was trying to relate these somehow. And in some sense, motivic theory is to find a category that lets you do all the things you do with the cohomology theory. And any cohomology theory satisfying these properties, there should be a function from that category giving you that cohomology theory. So I think here what they've done is they've said, well, there ought to be a class here, but because these coefficients are in Q, you can't have any transcendental things involved in it. And so by the time you get over here, that somehow forces you into to be algebraic here. And so that's what sort of led to some of this thinking.
Thank the speaker again.
Okay, so we have 2 weeks off due to the CUNY schedule. But on October the 2nd, which is a Thursday, David Marker is speaking.